three algorithms, gen, sign, and verify, where we sign a message with a secret key that's generated by a gen. Verification is done with a public key corresponding to the secret key. And we have the correctness requirement that any signature that was created with the secret key should be verified correctly with the corresponding public key, which means that the output of the algorithm verify is 1. And of course, we also looked at fixed length digital signatures with the usual restriction that we had several times. This was the schematic view. And we had this unforgeability and existential unforgeability of the chosen message attacks as our security model, very similar to message authentication codes, and we formalized that with a game, the signature forging game, and then the usual steps and the requirement that for all PPTs there is a negligible function that the algorithm can only win this game with negligible probability. We looked at RSA signatures as an example, and then we went on to actually construct these signature schemes, and for that we go via several steps, and we already saw the first step last week. So what we want to show is that digital signature schemes exist if and only if one-way functions exist. The construction at the end will be quite inefficient and it's not practical, but the intermediate steps and the constructions and the techniques that we use are very important as well. So, and we'll concentrate today again on collision-resistant hash functions, and in 2 weeks or so I will actually briefly mention that we can relax collision-resistant hash functions, existence of collision-resistant hash functions, to one-way functions. And what we already did last time, we looked at the first step is constructing so-called one-time signatures. And more precisely, even one-time signatures with fixed length. And then we now have to go from one-time signatures with fixed length to one-time signatures with arbitrary length. And those will enable us to construct then digital signatures that have our standard model of security, namely existentially unforgeable under chosen message attacks. So what was the difference between our original security notion, namely the existential affordability under chosen message attacks, and one-time signatures? Well, we only restrict for the one-time signature the number of queries that an adversary can make. In the existential unforgeability game, he can make arbitrarily but polynomially many queries. For one-time signatures, he is only allowed to make one query, and then he has to output a valid forgery. That's why it's called a one-time signature. One-time signature, if you just use a secret key, public key to generate one signature, you are on the safe side. If you use it twice, we don't know. And then we actually constructed a one-time signature, namely Lampert's signature scheme, where you actually can, I don't want to go into the construction itself, but it relies on just the existence of a one-way function. Okay? And it's really just a one-time signature. You can easily, and I think you do that in the tutorial exercises, see that if an adversary is allowed to query for 2 messages, you can forge any signature. Simply because then you can compute the complete secret key with just 2 queries. Now the important and the most important restriction in this construction is that this is for fixed length, for messages of fixed length. The way I defined it is if you choose a key of length, well, if you have input parameter n, then this is really just for messages of length n. That can be made more flexible, but still, in any case, you get something that has fixed length. And in any case, you get a one-time signature where the message length that you can sign is less than the key length. you can see that immediately here, the message length that you can find is defined by the number of columns here. But since you have two rows in the secret key, but with the same number of columns, the keys are always longer than the messages that you can sign. So, and that restricts these one-time signatures quite a bit. And hence, in our first step now in our construction of signature schemes is to get away from this fixed length restriction. And this is the first time that we use a really important construction in our overall construction of signature schemes. Namely, we use collision-resistant hash functions, and we use the hash then sign principle. And that is really an extremely important technique in cryptography, in theory and in practice. Okay, so to define the hash then sign, I briefly talked about hash functions last time already. Let me repeat that again. So a hash function is a pair consisting of two algorithms. The first one is a key generation algorithm that on input 1 to the n outputs a key from 0, 1 star. The second algorithm, H, is deterministic. It takes as input, as usual, the security parameter, a message from 0, 1 star, and outputs a bit string HS, X, which we also often denote H subscript S of a superscript S of X. And this thing is supposed to be in 0, 1 to the L of n. So the output is a fixed bit string, is a bit string of fixed length, whose length depends only on the security parameter n. It's L of n, but it's independent of the message length. So we kind of compress the message into something rather short. And L of n is a polynomial, it's called the hash length. And as usual, we can relax relax this condition that we can hash any message to the requirement that we can only hash certain messages of a certain length, L prime of n. But then we require that L prime of n is larger than L of n. So in any case, even if this here is arbitrarily long, or here for fixed lengths, in any case, the hash values are shorter than the messages. And again, then we call it a fixed length scheme. So ultimately, we want something like this. When we construct those things, usually we first construct something like this, and then by some general techniques, we go to this. Okay. And then we had our security requirement is collision finding or collision resistance. And as usual, we do that by defining a game, the collision finding game, which call between a challenger and an adversary. The common input is the security parameter 1 to the n. Then the challenger chooses a key uniformly at random using the key generation algorithm and gives S to A. So this is a difference to almost any other game that we saw so far and that we see in the future. Here, the key is given to the adversary. In public key cryptography, the public key is given to the adversary. Here, really, the key is given to the adversary. Okay, so there is no secret key in hash functions. The key is known to everybody, in particular to adversaries. And then, given this key, the algorithm A has to find two inputs XX prime or two arguments XXX prime in 0, 1 star or a prime of 0 to the prime of n. It's a fixed length scheme. And he wins the game or has found a collision if and only if x is not equal to x prime, but they hash to the same value. So x is not equal to x prime, but hs of x is equal to hs of x prime. Okay. But it's important to notice the adversary gets the key. So here the thing that we have to construct is not something based on anything that's secret. It's based on the sort of mathematical complexity of the function itself, or the function family. And for each s, we have a function, so it's really like more like a function family. And then we do the usual steps and call a hash function collision resistant if for every probabilistic polynomial time algorithm A, there's a negligible function mu, such that the probability that it wins this collision finding game is negligible. Okay. So in practice, what we do usually is, we have in the background, we have these keys and these key functions, but then one key is picked and that's used forever. For example, that's true for SHA-2. There is actually a key involved, but nobody cares about it because it's fixed anyway. But to make this a mathematical, meaningful definition, we have to include these s. If there was just one key, then this is easy. You just define a pair x prime, and then you output it all the time. Okay. So, and I will talk about how we construct these things in lecture probably in 2 weeks, something like that. For the time being, we assume that those things exist. Okay. And it's not known how to construct these things from one-way functions, but we will see that actually we can use it. 2 weeks also, we'll see that we can relax our condition a little bit. Then we know how to construct it. So for the time being, so collision resistant is actually stronger than one-way function, as one can easily see. But we can relax it. Okay, and then we can come to our hash then sign paradigm that is used in almost any practical and theoretical construction of signatures. So what is the hash then sign paradigm and the hash then sign construction? So we assume that we have some polynomial L. And we have a signature scheme pi prime with fixed length, with fixed message length, and that message length is L of n. Okay? And we also have a hash function whose hash length is also L of n. So L of n determines the message length for the signature scheme and the hash length for the hash function. We'll see why we need that. And then we define the signature scheme pi, this is the new signature scheme, by the following algorithms. The key generation algorithm of the new scheme on input 1 to the n, it uses the key generation algorithm of our original scheme to generate a secret public key pair sk prime pk prime. And it uses the key generation algorithm for our hash function to compute this s. And then it sets the public key for the new scheme is pk prime comma s, and the secret key is sk prime comma s. So s is included in both keys, so that's not the secret part of it. It's something that everybody knows. As I said, hash functions, they do not have secret keys, and here everybody knows the part s as well. Okay. So new keys, old keys plus key for a hash function. Now the signing algorithm on input 1 to the n, secret key sk, which can be written as sk prime comma s, and message m in 0, 1 star here I assume that this hash function can work with arbitrary length messages. So what it does first, it computes the hash value of m using the key s. That by definition has length of, and since the message length of our original signature scheme is L of n as well, we can now use our signing algorithm sig prime with the key sk prime to sign the hash value. And that is our signature. So instead of signing the message directly, we've signed the hash value of the message. And here you see why we need that these two things are the same, so that this here is impossible, they fit together. Okay? The output length of this must be the input length of this. And this requirement guarantees that. And now the verification on input 1 to the n and the public key pk, which can be written in this form pk prime s, is as follows. We get m comma sigma. Now the verification algorithm also computes the hash value first. And then it uses the verification algorithm of the original scheme to check that this sigma is a valid signature under this new method, this message that was given by the hash value. And since it also knows S, that's no problem. Okay? So it checks that sigma is really a valid signature on the hash value of message M. So hash then sign, instead of signing the message directly, you always sign the hash value. That is hash then sign. Okay. And then we have the following two theorems. The first one says is pi prime is secure and pi h is a collision resistant hash function. Then this hash then sign construction is secure. And we can also prove that if pi prime is only a secure one-time signature and pi h is a collision resistant hash function, then the resulting construction is one-time. It's a one-time signature, secure one-time signature. So if you start out with something that's secure, hash then sign collision resistant leaves gives you security. If you only start out with one time, you at least keep the one-time security. I will only prove this here. This is the same proof basically with a few restrictions. But then in our subsequent constructions, we use this. Okay. But this is it's the real proof. Okay. Okay. Okay, let's do the proof. And here, it's the second time that we see this combination of two primitives to construct a new primitive. And remember that when we had authenticated encryption, remember we had a CPA secure encryption scheme and a message authentication code, and together they gave us authenticated encryption and then CCA security. And in our security proof, we had to like split the proof into parts and say that if we can break the new scheme, we can break either this one or this one. We can break this one or the other one. Okay. So and similarly, we'll do this here. And then we have to combine these results to prove the security of this one. Okay. Of this construction. So we have to involve both schemes and both assumptions. Good sanity check in any proof that you do. Do I use all my assumptions? If you don't, either your proof is wrong or your theorem statement is not as it should be. So how would we prove this? The way we do this is the following. So A obviously is fixed. But arbitrary PPT in sign forge against pi, the new signature scheme. Yeah? Okay. If let m comma sigma be a message signature pair that A outputs with sigma being a valid forgery. Okay. And also remember that in our security game, the adversary is allowed to ask many queries, right? Here, right? So here in our forgery game, he can ask all these queries, right? So let Q M1 up to MS be the set of query messages that A used in this run. Okay? So now we distinguish the forgery that A outputs into two types. Okay, we define two types of forgeries. So the first one is there exists an I such that the hash value of HS of M is equal to the hash value of MI. Okay. So there is one query message that has the same hash value than the message that we output as forgery. And the second type is simply the first one does not. Not the first one. Okay. It's not. So not I. Okay. And we denote this event that this happens. We call this event collision. So in this case here, it's easy for the adversary. If we have such a collision, it's easy for him to forge something, right? Because the signature here is a valid signature for M as well. Because they have the same hash value, and by hash then sign, we just look at the signature under our old scheme on the hash value. In this scheme here, then we will argue that he really needs to break the original signature scheme. So this will be used to find collisions. This will be used to break the original scheme. Okay. And now I would like to erase this immediately, because then I will do how we use these two things. Then we'll go to our constructions or our collision finders and forgers. So now let's do what is the probability. This is the thing that we want to analyze. Sign forge of A against I on input N. This is the thing that we need to analyze. We want to show that it's negligible. Right? And as often we partition this thing into sub-events, disjoint sub-events that together cover everything. And the way we partition it is based on this event collision. So this is the probability of sign forge A, I of N, and the event collision happens, plus the probability of sign forge A, comma pi of N and not collision. Yeah. And this I can rewrite. This part I just copy. Okay. And here I use conditional probability. So this is copied, and then here I use the probability of sign forge A, comma phi of N conditioned on non-collision times the probability for no. Oops, this is the wrong way around. I will copy this here, sorry. And this I will write as with conditional probabilities, otherwise it doesn't make all that much sense. Okay, so and this above I rewrite as sign forge A pi of N condition collision times the probability for collision plus this part here. And this is upper bounded by, I ignore this term here, this factor here. So this is upper bounded by the probability for a collision plus, and now let me write it out again, the probability for sign forge A, comma pi of N is 1. Oops, he was always missing is 1. It's 1. So there was always just this 1 missing, right? Is equal to 1. This is probability that sign forge A, comma pi of N is 1 condition on collision times probability for collision. And so I just drop this and then I copy this from above and not collision. Okay. So if we can prove that this is negligible and this is negligible, then we are done. Because then this is negligible as well. And since was A was fixed but arbitrary, then we would have shown that for every probabilistic polynomial time A, there is a negligible function. Success probability is negligible. Okay. Good. So, and to prove that this is negligible, we use our adversary A as a collision finder to construct a collision finder. And here we use our A to design forger against pi prime, the original signatures. And we know that because it's collision resistant, then this thing here must be negligible, and because the pi prime was secure, this must be negligible as well. So that is how we are going to proceed. Yeah, structure clear? So let's go to our games here. Okay. So first, how can we, from the forger against pi, how can we construct a collision finder? And here is the way we define how we get this. Okay, so let A, our fixed but arbitrary adversary against pi in sign forge, and then we define pi h at hash collision as follows. And we can use this as a subroutine as usual. So A1 on input 1 to the n, and it also gets the key for the hash function, which is generated using the key generation algorithm of H. So then it chooses SK prime, PK prime for the pi prime itself using the correct key generation. And then it extends this key for the hash function using this pair for a public key, secret key pair for pi. Now this key pair, PKSK, is generated as in the real key generation algorithm for pi. Because in pi, we use this as it's done by the challenger sort of, and here we use it as the A1 does it. So it's correctly generated key pair for pi. Okay. Now we do the following. We simulate A with input PK. Now A is allowed to make queries for its for the scheme pi. Okay. But A1 is just a collision finder. It doesn't have any queries. Right? So it has to answer these queries all alone on its own. But as we'll see, it can do that easily. So we simulated whenever A, sorry, this is an A. This should be an A. Whenever A asks for a signature under a message M prime, we do the following. First, we compute the hash value of M prime. We can do that because we have the key S. It's one of our inputs. And then we compute sigma prime using the signing algorithm of pi prime using the secret key S prime, which we can also do because we know SK prime, which we generated ourselves. And then we return sigma prime to A. And this is a correct answer. It's exactly as in the forgery game. It's generated our keys as in the forgery game, as in the scheme pi. Now, eventually let Q be the set of queries made by A, and let M, S be A's answer. Then if there is an M prime in Q with H S of M prime is equal to H of S M, return the pair M, M prime, otherwise return failure. Good. Now, what's the success probability of this guy here? Now, the simulation of A is perfect. It's exactly as in the forgery game. We answer everything correctly. The keys are generated as in the forgery game. Everything looks as in the forgery game. So, and this finds a collision if two things are happening. Namely, it finds a forgery, and we have this here, and it has a collision. So this here, this guy here, I'm sorry, I don't even need that this is a forgery. It's just that it's collision. Whether it's a valid forgery or not, I just want to know whether whether we have a collision. So this here really is the probability of hash call A1 against pi H of N is 1. If this has found a collision somewhere, we're done. But we know that since this is obviously a PPT, if A is a PPT, so this must be negligible. So we just run it to get to get the collision. Any questions here? Yeah.
Maybe a stupid question, but we require that M is not contained in Q, right?
Yeah. Okay. So collision is also, yeah. So collision means M is equal to Mi, and M is not in Q. Sorry, I didn't write that down correctly, I think. So let me. So collision say. That's collision. Thank you. Okay. So that this part here, and now we need to analyze this guy here. So now we have to use our A to construct a forger against A prime. And again, A will, when we simulate it, it will ask signing queries. But this time we will be able to also use our challenge of against pi prime. So let A be an adversary against pi in sign forge again, and we define now an adversary A2 against pi prime in sign forge against pi prime. But this A2 has its own challenger, right, that it can query on signatures. but signatures on messages for pi prime, and it gets signatures according to pi prime, not pi. But as we'll see, that's easy to do. So I2 gets 1 to the n, it gets a public key pk prime, where sk prime, pk prime would generate it using the key generation algorithm for pi prime, namely by its challenger. Now, again, here we get this pk prime. We extend this pk prime to with a key for the hash function, which we choose using the key generation algorithm. So then forget about this part here. It really uses now the public key pk prime comma s as its public key for the scheme pk, for the scheme pi. Yeah. Implicitly, the secret key then is set to this here, right? But A2 cannot set it to this here. So that's sort of implicit. I should not have written it down this way. So really, this is only implicit. Right? But the public key now is generated correctly, as in the scheme pi. Yeah. Now we simulate A with input pk, which we generated correctly. Whenever C A, copy paste, ask for the signature M prime under this secret key, which it doesn't know, but it wants a signature under this secret key corresponding to this public key. That's why I said this is implicit. On a message M prime, we do the following. We generate the hash value. We know the key S, generated it ourselves. And then A2 can query its challenger C prime on input H prime to obtain sigma prime. H prime, remember how we required that the output space of the hash function is the message space for pi prime. So this is a legitimate message for pi prime. And A2 can query its challenger C prime on this message to obtain the corresponding signature. And then it returns sigma prime to A. So it plays this challenger for A, as we always need to do. And the signature is computed correctly, as in scheme pi. It's hashed and signed, according to this public secret key pair. Yeah. Now, again, let Q be the set of queries made by A, and then if A returns a message M comma sigma such that H of S M is not equal to H of S prime for all M prime in Q, which implies that the M is not in Q, right? We return the pair HS of M comma sigma, otherwise we return failure. Okay. Now, what's the success probability of this algorithm? And I claim it's a success probability that A2 finds the correct signature. So, sorry, that A finds the correct forgery, and there was no collision. Why do we need that? Obviously, that it has to find a valid signature, a valid forgery. Otherwise, we do not output a valid forgery for pi prime. why do we need that also this is true? If this is true, then A2 never queried its challenger on the message pair it output, on the message it output as in its forgery pair. Or the other way around, if there is a collision, then this here is not a valid forgery for A2 because this message was queried. That's not allowed. What the message space for pi prime that A2 attacks is the hash values of HS. But if it's not true, if there's no collision, then it never queried its challenger on the message H prime, and we are done. So this here really is then the probability that sign forge of A2, pi prime n is 1. And since we assume that this is pi prime is secure, this must be negligible. This here was already shown to be negligible because H is a, or gen pi H is a collision resistant hash function. The sum of two negligible functions is negligible, and we are done. So the last part is a little bit subtle maybe, but we really need that we did not query this, our challenger C prime on this message on the hash value. And that's why we require here and not collision. We just partitioned it. So it all boils down to our distinguish between the two types of forgeries that A can generate. Okay. So hash then sign is secure. And you can easily see that, yeah, obviously this theorem will also be true. To change nothing. Just make one query, and that's it. Okay. Questions about this? So before we go into the break, this time today we make the break a little bit earlier. So now, what we now do, we would like to go from one-time signatures, which we now construct for arbitrary length. So that was one-time signatures fixed length was Lamport scheme. Now with hash then sign, we have one-time signatures for arbitrary length. Now we want to remove the one-times. As an intermediate step, we have one more intermediate step. We construct so-called stateful signatures. And from one-time signatures, we construct stateful signatures that have another limitation, not one-timeness, but it's the statefulness. And then we'll remove statefulness using pseudo. And let me just tell you what stateful signatures are. In a stateful signature, we have stateful signatures is also a triple of algorithms, and the key generation is as before. The signing is different. The signing algorithm on input 1 to the n secret key sk it keeps a state, ST, and it outputs a signature when we give it a message M prime, state and signature S and a new state. So the signature on a message now depends also on the state, which implies that the signature may depend on all previous signatures that I constructed as a signer. So I keep in mind how I generated my previous signatures. And then the new signature depends on how I created my original signature. So that's why I include the state here. Now the verification algorithm is as before. So the verification does not need the state. So you should be able to verify a signature without knowing the state, just getting the signature. Signature may be quite long, including some information, but you don't need the state itself. And what we require for stateful signatures is the usual correctness requirement. And we require that the state doesn't grow too fast. So you always want to, if you already started out with a state, then you want that the new state grows only by an additive term, which depends on the length of the message that you signed times some polynomial. So the state should not grow too fast, so that you can sign polynomially many messages and the state is still polynomially large. This is satisfied if you do that. Originally, the state is typically empty. It's just the empty string. Okay. So the important here is the verification does not depend on the state. Here it does depend. The signing depends on the state. Typically, stateful signatures are not very practical. You don't want to remember all the signatures that you ever created to sign a new document. That's not what you want to do. In some cases, actually, statefulness is okay in some applications, but typically it's not. We use it just as an intermediate step. And see that we can use it to construct secure signature schemes. Security, the definition stays the same, except that, well, the requirement is the same, but in the definition of, in the sign forge game, C, the challenger, is the one that always signs things, right? It answers the queries by signing stuff. So it has to keep the state as well. So it's something internally to the challenger. But the game from adversary's point of view looks the same. But the challenger has to use that. Okay. Here, maybe I do the warm-up. That's actually easy. Here's an easy way to get a stateful signature scheme, but that's very inefficient. So assume you have a signature scheme already, and let L be a polynomial. And we define the stateful signature as follows. The new pi prime, the new scheme, it simply generates L of n many key pairs using the key generation here. Okay. And then, so the secret key now consists of the sequence of sequence key, the public key consists of the sequence of public keys. Now, if it wants to sign a message with a state, then it simply the state here now is simply how many signatures did I already compute? Yeah? Or what's the number of the signature that I now compute? So that's the state start with 1. So the signature that I next construct is the first one. And hence I use my first secret key. Then I increase the state by 1. And then I use the next secret key from my list. Okay? And so on. The verification, you get the public key, you get a message m comma sigma. You just check, is there an I such that this sigma verifies under PKI? So is there a public key in that list that verifies this signature? Okay. Yeah. Why is that useful? Well, if we want to use, so here what I said, if I only want to sign L of n many messages, I'm fine. If I'm asked to sign more than L of n messages, I give up. I can't do that. This is here because if state is less than or equal to L of n, I output something, otherwise I output the failure symbol. So this is a correct signature scheme as long as I only need to compute L of n many signatures. Now the interesting thing is every secret key is used to sign just a single message, right? By construction. Hence, if my original scheme is a one-time signature, then this is the signature scheme. Because I guaranteed that I only use every secret key from pi just once. Right? So this is the typical thing that we do to get from one-time signatures to statefulness. So that's why it's useful to have the statefulness. But this is a very wasteful signature scheme, right? You need to know how many signatures you want to sign in advance, and then you have to compute these huge secret and public keys, and the verification is really, really bad, right? Because you have to check every single public key whether it fits. Okay. So it's really wasteful, but it shows you why statefulness can be useful. To get from one time to arbitrary signatures. The state is there to guarantee that you only use every secret key once. And after the break, we'll discuss how we get around these wasteful signatures. And also the requirement that we need to know an upper bound on the number of signatures that we want to generate. But I'll do that after the break. And we'll see two constructions. One is called the chain-based construction. We will not use it later on, but it's important. It's used in blockchain. That's actually the main technique, and kind of hash then sign plus this from a cryptographic point of view is the main technique in blockchain. And then we use a tree-based construction, and that is incredibly important. We use it, but it's also in Merkle trees and all kinds of authentication things. This is the thing that people use also in practice. Okay, but first we do a break. Let's do a 15-minute break. Okay, then let's continue. So we want to construct these stateful signatures. questions about stateful signatures? So that we keep a state of what we did so far. Okay, so we want to get around this wastefulness of pre-computed keys, and there is an important technique to do that, which is often called the refreshing paradigm or refreshing keys. And the refreshing paradigm uses fresh instances of a signature scheme for signing new documents. This is what we did for pre-computed keys as well. We used a new secret key all the time. However, we don't generate them all at once in the beginning. We use them as they are required. But then we need to tie them sort of to the original secret public key. And we do that by authenticating them using the original one. Okay? And this authentication may actually be indirect. So there will be a kind of a chain or sort of some connection of the new keys to the original and the original public secret key pair. Actually, this way of authenticating keys is actually the technique that we also use for certificates. So it's really important. And to make this more and we will see two examples. The first one is mainly there to get used to the techniques. As I said, it's also used in blockchain, but for us, the second one, namely the tree-based version, is much more important. And in doing this here, this authentication, you will see why we had to go from one-time signatures of fixed length to one-time signatures of arbitrary length, because we need to be able to sign long messages. Not necessarily arbitrarily long messages, but really long messages. I already said all this. Okay, good. So let's look at the chain-based signatures. So let pi prime be a signature scheme that can be used to sign messages of arbitrary length. And it's always good to imagine pi prime being only a one-time signature. So we want to use secret keys in this one time for this scheme only once. Okay? So, but at the end, we want some signature scheme that is not one time, but will be stateful. And then we define a stateful signature scheme as follows. So our key generation algorithm simply generates a key using the original signature scheme of the key generation algorithm of the original signature scheme. So that's SKPK. So our this is really our secret key public key pair. One pair, period. But we also have this state. And now the state will be much more complicated than in the pre-computed key case, where it was just an index or a counter. So here we set SK1, PK1 to be SK. Keys in the beginning from the key generation is simply SK1, PK1. Out of all is a list that's originally empty. So, and then the state is 1, keep a counter. The keys, it's a list of pairs, and out. So the secret key, public key will be this, and this is a state now. Remember, stateful signatures, we have a key pair, and we always have a state. now comes the signing key. So assume you already have signed I messages. Okay. So you have sign on input gets this secret key. The state in general will consist of a counter, a list of keys, and as you will see, auth will be also a list of things. So now you want to sign a new message with this state, given this state and the secret key. Now you pass the keys as a list of secret key public key pairs. SK1, PK1 up to SKA, PKI. You choose an I plus first key pair using the key generation algorithm of the original scheme. And you do the following. The signature now is you use the signature scheme of the original scheme, sign the secret key that you use is SKI. What you sign is M concatenated the new public key that you will use for the next signature. And then you said the keys now, the list of keys is you concatenate the new pair that you generated. All the authentication list consists of the old one, and you concatenate M PKI plus 1 sigma prime. The sigma prime authenticates all these things. And the signature, the real signature one, consists of this stuff here. The new authenticated list, the new authentication list. Okay. Yeah. Okay. Good. So the signature on a message consists of all the messages that you signed previously. It's not so efficient, but never mind. Okay, so how do we verify? Verification, you get 1 to the n, you get PK, you get sigma, a signature. Remember, sigma is an authentication consisting of auth 1 to auth I. Each entry is of this form here. MJ, PKJ plus 1 sigma J prime. So return 1 if and only if the first public key in that list here is the public key of the signature scheme, the overall signature scheme. And for all J, you check that this signature verifies this message here. The combined message, the concatenation. So let me write down a little bit. So you have SK or PK, SK, which is also the first entry. Then using with SK1, PK1, you authenticate M1, PK2 using this sigma 2, sigma 1. Right? Now this PK2 sort of is authenticated with PK1. So now you have sort of here a link to this SK to PK. Always change the order here. and now you have at least BK2, SK2, and this here is authenticated with this guy here. This here then you use to do M2, BK3, sigma 2. And then sort of you can do here, authenticate, you get BK3, SK, and then you use that to do M3, BK4, sigma, and so on. And what you check here is, sort of, this is authenticated using this here. But this was authenticated using this here. This was authenticated using this here. And this is the original one. So it's this indirect authentication. This is what I mean. But eventually, using this chain, the sequence of things, you go back to this root, sort of. Okay. So, and then if you want to forge, you have to forge something in between. At some point, like you want to forge something, you would have to forge one of these signatures here. You want to sneak in a new public key that was not certified, and you have to sneak in some. I don't want to go into the proof, but formal proofs, but pi as defined above is a signature scheme. If there is a polynomial p such that for all n and all keys, at most p of n signatures are generated with a key. But we don't need to, again, why do we can only sign polynomially many messages? Why is that? Can you see that why we cannot sign more than polynomially many messages? All our algorithms must be PPT. If you want to sign more than polynomially many messages, the signatures will become super polynomially large. Verification will have to check all previous signatures. More than polynomially many, you can't do that. But unless the previous construction, you need not know this polynomial in advance. It's just that at some point, things also in practice, things just become too large. You include all messages. If you sign messages of megabytes all the time, you sign too many of those, bad. Because in our signature, all previous messages that you signed are included. That's really bad. But on a theoretical level, we have this observation. And we have also the following observation that in the chain-based signature, each key pair is used to sign at most one message. Right? The ith secret key is used to sign the ith message consisting of the ith message and the I plus first public key. But it's only used one. And that can be used to show that if pi prime is a secure one-time signature, then pi is a secure stateful signature scheme. The proof is not too difficult. It basically uses index guessing and things. If you forge a signature, you have to forge some point in between here, and that doesn't. At that point, you have to forge something in a one-time signature scheme. So that doesn't work. Okay. Yeah. 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 That's true. Yeah. The key generation, but that leads to an interesting question. In a secure signature scheme, that cannot happen with significant probability. Because that would, if that happens with significant probability, that would imply that you only have polynomially many secret public key pairs, possible secret and public key pairs. If you have only polynomially many secret public key pairs, the scheme is not secure. So yes, so this happens only with high probability. In the signing, you could also check that you did not use that thing before. If you were really unlucky, and then try again. That makes the analysis harder. I would not recommend doing that if you want to analyze it, but it works. Okay. Okay. Yeah. Good, but you can see that this thing has two really, so one big disadvantage. Signatures are really, really long. And the reason why it's long is that it depends on our previous messages. And we would like to get around this. Also, we would not like to include all these M's in. Now you go back to data structures and algorithms. One thing is linked lists. If linked lists is not what you want, you go to trees. Sort of theorem 0.1 from computer science. If you don't like lists, go to trees. And that's actually what we do, and that has many advantages as well. So, but and I will explain those in more details when we've seen this. Okay. Yeah. Okay. Good. Okay. Anyway. Okay, let's go. So we want now to have these tree-based stateful signatures. And as before, we have pi prime, which is a signature scheme that can be used to sign messages of arbitrary length. You see that this construction would not work if I use a one-time signature with fixed length messages like Lamport. Because what I need to sign is longer than the key. I need to sign in particular a key itself, but then additionally some message. So this would not work with Lamport directly, because Lamport would not be able to sign its own public keys. They are too long, because public keys in Lamport are longer than the messages that we can sign. So it would not work. That's why it was important that we went from fixed length to arbitrary length. And here we really need we want to sign arbitrary messages, then we need that. Okay, so the tree-based signatures. Key generation algorithm, stateful signatures, we generate the keys and we generate the state, the initial state. Okay. As in the chain-based, our key generation uses simply the key generation of our original scheme pi prime. And then it also has a list of keys as before. We will index them, though not with numbers, but with bit strings. Why? Well, in a chain, you have indices, counters. In a tree, you have sequences. So you have sequences of bits telling you where in the tree you are. The root is empty, has the empty index, the empty string as an index. The left and right child are 0, 1. And then the right and left child of 0 is 0, 0, 0, 1. Left, the children of the left child is 1, 0, and 1, 1, and so on. So the indices tell you which path to go in the tree to end up in that node. Yeah? And the key and secret key public key pair is the key that we store in the node, in the root, sorry, in the root. Okay? Keys is initialized with just this pair. We have again this authentication list, which is initialized to be empty here. And the state consists of keys and authentication list, but not messages. There also in auth there will be no messages in the beginning. Okay. So we kind of have here a root, and say here we have pk epsilon sk. Oh, this sits in the root. Now, this is a signing algorithm. We build this the tree-based thing. We will be able to sign sort of on security parameter n. We will be able to sign 2 to the n many messages. Okay, if n is large, that's exponentially large, so we don't need to worry about that we don't have enough space to sign all our messages. And if we have, so we will look at the tree with depth n. The messages correspond to leaves. Okay? So at the very bottom. And sometimes it's easiest to imagine that this is 0, 1 to the end. The message space is 0, 1 to the end, but I will tell you that this is not necessarily the case. We can easily adapt it. So we can all sign all messages from 0, 1 to the end. It's okay. So in each message here, check which one, what number I used here. Oh, I did even 1, 2, 3, 4. Wow, that was ambitious. So we can imagine here having 16 messages. So Okay, this is our tree. Here we have the messages. Okay, and say, just check that I didn't do it differently here. Okay, good. So left from your point of view is always 0, right is 1. So you can imagine that we have labeled edges. And here at the very end down, we have here 0, 0, 0. Here this is 0, 0, 0, 1, and so on. Okay. Now you want to sign a certain message. Say you want to sign a message 0, 1 to the end, with M1 through Mn being its bits. Okay. Okay. Now what you do is you, let me do it here. Here say we want to sign this message here, 1011, 1011. Okay, this is this guy here, 1011 here, 1011. Okay. That sits down there. Okay. What we do now is we go down the path to this node, to this leaf. Here, here. And now we check each interior node will have secret public key pair and a signature. Okay. And it will contain, so here SK1, PK1, and so on. These are all indexed with the corresponding description of the path to that node. Here it's just 1. Okay. And it also contains a signature. And the signature it contains is the signature on the public keys that sit in its children. So here is 0, 1, 0. This is this public key. And here 1, 0, sorry, 1, 0 here. Okay. 1, 0, this guy, 1, 1, this guy. And so in each node, we have a public key, secret key pair, and in each node also the signature on the public keys of its children with its own secret key. Okay. Yeah. Okay. So imagine first that we fill out this complete tree with all the required information. Okay. So we choose the public key, secret key, public key here, 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 for all of them. And then in each node, we sign the public keys for the 2 children. Okay. We do that for all interior nodes. The leaves contain the messages. Yeah. And they also contain a secret public key pair as well. And but this guy here, it contains a secret public key pair, but the signature it contains in the signature on the message, so on the index of that leaf. Okay. So here 1011, PK 1011, and it signs this message 1011. Okay. So now you can think of, you fill out the complete tree. You don't want to do that, but conceptually, that's actually what we do. Okay. Why don't we want to do that? Exponentially large, 2 to the n. Right? So when we actually use the scheme, we generate things as they are required. So we don't fill out the whole tree, but when we want to sign this message, we go down this path here, boom, down here, and then we look in each node. Did we already generate the public key, secret key? If not, do that. Also, we need to be able to generate the nodes, the children of anything on that path. So if you go down here, dum, 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 because in this node here, you also have a signature on the public key here, not just here, which is on the path down here. So you have not just to generate all keys on the direct path, but also on the direct descendants from that path, if they do not exist. If they already exist, they should be stored somewhere. Where are they stored? In the state. The things that we already generated are stored in our state. So that we don't have to generate this complete tree from the very beginning, but we do it as required on the fly. And that leads to this beautiful signing algorithm. So you want to sign this message here, M1 through Mn, which is a bit string. For I from 1 to n do, you go down the path to that leaf. If for b in 0, 1, sk m1 m1b is not in the keys, choose it for you. This is the thing on the path. You go sort of upwards. From the leaf, you go upward. You start with 1, then for each iPhone. No, you don't do that. You go downward. Go down. 1, you just check I is 1, so you just check have the 2 children of the root. They already been assigned secret public keys. Those 2 things you always need, because one of them lies on any path to a leaf, and we also need the direct descendants as well on the path. If not, you choose it and add it to keys. And also, if a signature on to, if this has been sort of, it may happen that you have already generated here something, you generated here, now you need to generate here, and then you also have to generate the signature. So you also generate the signature that each parent stores the signature on the public keys of its children. And if they are not yet there because you did not need to compute them so far in your signatures, you generate them and add them to the stuff. And eventually you compute the signature at the top. And the authentication of the signature consists of all these authentications that you need. These are all the nodes on the path to that leaf. And these are exactly the ones on the path. You go down here, you have the authentication here of the public keys here. You have, if you go down here, you have here the authentication of these 2 public keys. You have here the authentication of these 2 public keys, and then you sign with this public key. It's a little, in terms of formulas, a little bit complicated, but the idea is very simple. Just do everything on the path. And that's it. But we always generate things only as they are required. which means that if we only sign polynomially many messages, we'll only sign polynomial, this thing will only be of polynomial length, because each path is of length n. On each path, we have n+1 nodes, plus the direct descendants of the path, which give you another n. And the verification is simply done. You pass this authentication, you check that everything fits, and at the end, you verify the signature as well with the verified public key at the end. And that's what written down. These two are generated this year, and this is this. So the public key here and here are verified using this year. The public key in here are verified using this year, but this has been verified using this year, so it has been verified using certified using the original root public key. You only need to do this on this, also on the level of children, parent children. No? Okay. Yeah. So, but always keep in mind, fill out the tree according to these rules, but then do it only as required. The actual sign. And you see here what I already depicted there. Again, if what I can show is if pi prime is a secure one-time signature, then pi is a secure state for signature scheme for messages of length n. You use every secret key just once. The secret keys in an interior node is just used to sign the messages consisting of these two public keys. And the secret key used for stored in the leaf is used to sign the message, but nothing else. And that's good enough. The formal proof is a mess because there are so many indices involved that you don't really want to do. And this is the key observation that we have. Okay. I wrote down how you get from forgery in pi to forgery in pi prime, but check it if you feel like it. But this actually is not too bad that you can get this, but anyway. Good. Instead, we should look at how we actually, what's the advantage of this tree-based compared to the chain-based thing? Okay. Now, the first big advantage that we have is that recall in the chain-based, this signature scheme consists of all these authenticators plus the final signature. But the authenticators are just signatures of a pair of public keys. They do not include the messages. Very important, they do not include the messages, and they do, so that means also the public keys usually are much shorter than messages, so it makes things much shorter. But as we'll see, it also has another important property or consequence. not a property, it's a consequence. Okay. Second, the list of authenticators here are much shorter than in the chain-based. In the chain-based, it depends on all previously signed messages, the length. Here, it's only logarithmic in the length, or it's on the path. So roughly speaking, it's logarithmic, sort of, what you do. Again, much shorter. Fewer elements are shorter. Very good. Yeah. So this is, by the way, you don't need to sign just messages in 0, 1 to the end. View these are just identifiers for messages. The message itself could be anything. Just an identity. This message gets this identifier. Then you have to check, well, which identifier did I not use so far? I give that identifier, and then I send a message down there, complete message. Just saying, okay, but this is the identifier. So that's also quite nice. Okay, good. So that's the trees. Okay. In the state, remember, because this will become clear, in the state, we keep all the public keys that we also generate. Because we added 2 keys to this list here. And that is the so that's the state consists of keys and authenticators for pairs of public keys. The intermediate authenticators. Only if you go to the bottom that you add this signature on the message. Other than that, it's just signatures on public keys. Okay, so we have, if we have one-time signatures, we can construct stateful signatures. And if you use this idea with identifiers, even on arbitrary length messages. Now we want to remove the statefulness. Okay, so how do we remove the statefulness? We use the following idea, which goes back to what I just said. Here, when I go down this, I need to generate the key with the key generation algorithm. And I generate it with some randomness. Hence, I have to remember what these things are. Okay. Now, instead of remembering the keys directly, I could just remember what is the randomness that I used in the key generation algorithm to create this key. When I run this algorithm here, this is a probabilistic algorithm that gets as input 1 to the n, but internally it uses randomness to generate the keys. If I just remembered instead of the key, the randomness that I used to compute the key, then that would be also good enough. Because then if I want to know the key, I know the randomness, I just start my key generation algorithm with that randomness and it reproduces, then it's deterministic, it reproduces this key. So now, why don't we just use pseudo-randomness instead of randomness? If I use pseudo-randomness that depends just on the position of the node, I can recompute the keys as they require. You tell me this is a node, okay, then you use this pseudo-randomness, I use that, feed it into the key generation algorithm, get my key back. And I don't need to store anything. Just the seed for my pseudo-randomness. And that's exactly what we do. So we use instead of the true randomness in generating key pairs and signatures, we use pseudo-randomness, and this way key pairs and signatures can be again recomputed as needed in the tree-based construction. More generally, or more precisely, what we do, we have a pseudo-random function, as we had them before, such that for all n and all r and 0, 1, n, we have that if 0, 1 to the is a bit string of length less than n plus c, then it gets some length L of n, where c is a constant and L is a polynomial and stuff like that. And these algorithms on inputs of length n use at most L of n random bits. Okay. So the function produces basically L of n pseudo-random bits. I'll explain this later in a second. Okay. So this here produces this random bit, L of n random bits, which can be used here and here as a random seeds to run these algorithms. What does this n plus c mean? Where does this come from? Gen obtains also chooses this r and this. We also use this, and what we do is we use this r. It's a random seed, and that is included in our secret key. Okay? So we use the key generation here that gives us sk prime pk prime, and also use this r as a seed sort of, or an initial seed for our pseudo-random functions. And the seed is also secret. It sort of gives you the information used to compute the pseudo-random that only you should be able to recompute. Okay. This explains this n here, but there is a c in there as well. And what we do is when we want to generate such a key pair at the position m1 through mj, mi through mj being bits, we call gen prime 1 to the n, fixing the internal randomness of AFR to m1 through mj. And fr, this is the index of the pseudo-random function, that's the randomness. And we include this, we need this for a key generation algorithm. Okay? Because at each node, we need to generate the randomness to compute the keys and to compute the signatures, in case we use a randomized probabilistic signature algorithm. Go back here. In each node, you generate a key pair and you generate a signature. Both may use randomness. Okay. Okay. So what this here says is it here? It says in node M1 through MJ, that specifies a node in the tree. And if you want to generate keys, key gen, use this randomness, using F with index R on this input. Gives you L of n bits. Yeah. If you want to compute the signature, you do the same thing, except that here it says, this is the randomness for the signature in this node. Okay? Where the sign is some symbol different from keygen symbol. And that explains this here, less than n, all internal nodes, bit strings of less than n, and the C is just there to encode key gen and sign to differentiate between the two purposes for which you use the pseudonym. And that's it. And then you just, the security now, if you do that, follows from the security of the stateless thing and the usual stuff. If it's good with true randomness and you have a pseudorandom function, it's also good for the pseudorandomness. Otherwise, you could distinguish between the pseudorandomness and the true randomness. And you are done. Okay. Yeah. You could not do the same trick with the chain-based construction. It's one of my favorite, more involved questions in an exam. Why can you not do that? I give you the answer, maybe you will remember it at some point. The thing is, in the internal nodes, I only need public keys. And I regenerate the public keys using the randomness, the pseudo-randomness. In the chain-based, internally, it's messages that are included. I cannot regenerate the messages. They are not generated using some key generation algorithm or so. They are generated by the user with some purpose in mind. I cannot regenerate them. Here I can because I only sign these keys that are independent of the other messages. And those I can regenerate using pseudonym, not if those include the messages itself. So it's not just that it's more convenient, more efficient to some extent. For the removing of statefulness, the pseudorandom idea, tree-based is the only thing that works. Chain-based does not work. Okay, good. So that leaves us with what we wanted. We started out with one-time signatures of fixed length. Use collision-resistant hash functions to remove the fixed length thing. Using one-time signatures on messages of arbitrary length, we were able to define stateful signatures. We needed that the length is not tied to the key length. Okay. Then we used the refreshing paradigm to remove this, to get from one-time arbitrary lengths to statefulness. And then we use pseudo-randomness to remove the statefulness in tree-based. In the different steps, we used 3 different techniques that are very important. Hash then sign. Really important. Chain-based things, for example, used in blockchain, but also in other authenticators. Tree-based, used in all kinds of authenticators, Merkle trees, in also in revocation schemes and all kinds of things. We usually use these tree-based things, often called Merkle trees. So it's really, really important. Yeah. Okay, good. Questions? What we did not see, what this does not show, is that we can construct secure digital signatures from one-way functions because collision-resistant hash functions are not known to be constructible from one-way functions. In 2 weeks or next week, on Thursday, I'll explain to you that you can replace, because when we use the hash then sign on one-time signatures, there's just one query that can be asked. Maybe we don't need collision resistance, the full power of collision resistance. Maybe we can weaken that. And the answer is yes, we can actually weaken that to something called universal one-way hash function. And if we do the same trick, hash then sign, on one-time signatures with universal one-way hash functions, we still get secure one-time signatures. And universal one-way hash functions can be good. So it doesn't make sense to combine in the hash then sign arbitrary signature schemes with universal one-way functions. But for one-time signatures, that is the thing that you only need. Okay? And we discussed those universal one-way functions when I talk a little bit more in detail about collision resistance and stuff like that. But before we do that, we'll go on Monday. Monday afternoon is another lecture. I go back to RSA. Remember, RSA is not secure. We can make RSA secure with hash then sign, but there, to make it secure, we need stronger properties for the hash function than just being collision resistant. Because hash then sign assumes that we start out with a signature scheme that's secure. And collision resistance is there to preserve security. RSA is not secure. So if we just combine it with something that preserves insecurity, that doesn't give us anything. So we need to do hash then sign, but with a hash function that has much stronger properties. And in fact, we do it with something that does not exist, but is a very important technique. In theoretically, it does not exist. Practitioners think it exists. It's called the so-called random oracle. Another important technique in cryptography, which says that like, random oracle is a idealization of a hash function. It's as good as it can be. It's like purely random stuff. But then combining with RSA, that's good enough. Okay, then that's it for today, unless you have questions or remarks. Doesn't seem to be the case. Then on Monday, the lecture is at 4 in the afternoon. Okay, good. See you then on Monday. Thank you.